lossless data compression. This mostly involves working at the lower levels, more bit and byte wise as it goes. And so yeah, let's get into it. The first one we're going to go over is called Huffman coding. Huffman coding, I've drawn up an example for us to go through right now. It's also known as the tree method. In this particular example, we're going to be working with an imaginary picture here that has light levels from 0 to 7, just to make things easy. Now, normally, if we were representing 0 to 7 in binary, it would require 3 bits per pixel, for a total of 75 bits to represent the entire picture. But maybe with Huffman coding, we can do a bit better than this. So to start Huffman coding, you want to first list the probabilities for each light level in the picture. So I've went through and did that in the table here. In the center column, you can see how many times each light level came up in the picture, and the probabilities in the right-hand column. Next thing you'll want to do is order them by probability. So in the table on the right here, I have organized the most probable light level to be at the top, which in this case was light level 3. And you can see they're in descending order there. Up next, we need to start at the lowest probabilities and start combining them. So down here, light levels 5 and 6 both have a very low chance of appearing in our picture. So what I did is I combined the probabilities of them, and then I reorganize it among the other probabilities. So when you combine the probabilities, you have a probability of 0.12, and you can see I've aligned it up with the other 0.12, and I have 5 and 6 here to represent the fact that they are now combined. And so what you want to do is you want to continue this process. So I combined 5 and 6 into 560 with a 0.2% chance. And of course, I reorganized up here with the 5s. And then you want to repeat this process over and over again until you are left with just 2. So we have this, we have these 2 probabilities down here. And now we kind of want, now we're going to get into the tree part of this method, which involves working backwards kind of from what we just did. So we're going to start here, and the last thing we combined was the 3 and the, so we start with 2 branches. So we have the 0 bit leading to the 741, and the 1 bit heading over to the 56023. Okay, so the last thing we combined was the 3 with the 5602. So that's going to be the first thing we break up. So here you can see I split off the 3 from the 5602, and that would be the end of that step. Continuing on, the next step, we broke off the 1 from the 74, and the 7 and the 4. So you can see I did that right here. And we kind of continue working backwards from our tables, splitting up each one like we did before. And eventually, you'll have constructed a full table that we are now going to use to encode the entirety of the picture. So dealing with this tree, you read from the top to the bottom. So if you were trying to represent a 2 in the table, you would start at the top. You go down the 1 path, down another 1, and into a 0. So the 2 would be represented by 1, 1, 0. A 5 would be represented, if you travel down the right side, then here you get a 5. You'll see that a lot of the different numbers have different lengths. Like a 3 goes a 1, 0, and that's it. And some of them are a lot longer. And we'll look into why that is in just a moment. But if some of them are being represented by 5 pixels when they were represented by 3 before, is this really better than it was? Well, let's look into that a bit more. So I went through the tree and I wrote down the tree code for each light level possible in our scenario here. And I've also went through and total number of bits for each one. And so there are two, for one number, light levels 1 and 3, we're going to actually be saving bits there. But for all the other ones, we're either breaking even or gaining bits. Well, it turns out, since 1 and 3, the 1 and 3 bits are the two most popular bits, it ends up working out for us by saving us bits. So in this table here, I went through and took the frequency of the bits in the table, multiplied it to get the total bits required by each light level, and then I summed them. And when we do, we get a sum of 72 bits. Now the 72 bits is very slightly better than the 75 from before. And it gives us a compression ratio of 1.046, which you can do by doing the 75 divided by the 72. Now, you may be thinking this is rather insignificant, but there are a few things about this example that make it that way. And the first is that we used a very small data sample. We used only 25 pixels, which is just a blip when it comes to actual image sizes. And of course, I used data that was relatively well spread out. If you have a more biased image, which is one that is like primarily a dark image or something like that, then the image will be a lot easier to represent in this manner, since you may not even need to include, say, 0, 1, or 2 light levels in your compression. But this is kind of a strange method. Why does it work like this? Well, like I said before, it's because the more frequent numbers need fewer bits. And this is all based on a concept from information theory that if the less likely an event is to occur, the more information it will convey. And so it's kind of representing that, because if a less likely event shows up, then we need to take more bits to convey it. Otherwise, we're just being very inefficient. Now, I said I had another method to go through, and that one is called arithmetic encoding. So for this example, we're not going to bother dealing with the picture, but we're going to be transmitting the message BAC. Now, normally this would take 3 bytes, but in our particular example, let's say that A has a 25% chance of occurring, B has a 50% chance of occurring, and C has a 25% chance of occurring. To do arithmetic coding, at least to understand it, it's simplest to start with a drawing. So you can see here on the right, I have drawn to scale the A, B, and C in a bar, much like you did when we first learned fractions, most likely. And next up, we want to go inside the B range, because that's going to be the first thing we're encoding. So once we're inside the B range, we want to keep the boundaries, but then we also want to calculate new probabilities. So we still have a 25% chance of A, but now that 25% chance is within the first probability of B. So that would be the 0.25 to 0.375 here, you see in the second picture I've added. So that means that anywhere within, with this coding method, any value between 0.25 and 0.375 could represent a sequence that begins with BA. And anywhere between the other values would mean a similar thing. So continuing this process to code BAC, you can further break it down into even smaller sections. So to code BAC, we can really use any value between 0.34375 or 0.375. If we only need to go three digits deep, that means we can use a value as simple as 0.35. And that's just 1 byte, so it can be a lot more efficient to use arithmetic coding when it comes to shorter sequences like this, compared to just using ASCII or some other kind of method for storing a sequence of letters and such. And that's really the 2 primary methods of lossless data compression. So I hope you learned something, and have a great rest of your day.